So this is the energy engineering lab that's covering liquids handling and some of the liquids properties. So we're going to look at both diesel, jet fuel and biodiesel, but of course there are other alternative fuels. The rationale for this is both economic and environmental. So there's been large growth in Asia, and so this has increased the demand for transportation fuels. These are internationally traded, and so if the price goes up because of demand, it is felt worldwide. There are some stranded locations where it's isolated or where production is so high the prices are artificially kept low, like Saudi Arabia, but essentially the more people are using our traditional transportation fuels, the more expensive that's going to get. Energy security, of course, is the third issue there. Certainly we were at one point in time highly reliant on imported crude oil. That has now changed primarily due to policy and taxing incentives that encourage the US to extract more of their domestic crude oil and natural gas, and a change in technology that allows us to reach more of the materials. But certainly we are concerned about energy security, and many other nations are, but we have taken care of that primarily not through switching to alternative fuels, although that certainly does play a role, but more extracting more traditional fuels, i.e. petroleum, in the United States. Greenhouse emissions are, of course, another significant issue. We're starting to get regulations in place, and so things like increasing the miles per gallon, which requires vehicle changes, are certainly come into place to aid our environmental challenges. And it's not just greenhouse related. There are also environmental regulations on the fuel, things like benzene, things like soot emissions, etc., etc. But certainly the greenhouse gas emissions are high, and if you can use renewable sources, then of course that would reduce our greenhouse gas emissions. So we use a whole variety of fuels for electricity, and of course this is a little old data. I'll show you newer data in a minute. But when it comes to transportation, we're dominated by the petroleum products, the portion on the left. When you go and look at the sources that we use for alternative fuels, it's the sort of biomass type of endeavor, and perhaps natural gas, and perhaps electricity as well. So if we go and look at last year, again, not much has changed. We've had a boost in the use of renewables for electricity, a little bit more of an increase in natural gas, and renewables are coming into play, but a very, very small percentage of the total fuel supply. So we're still primarily petroleum based for our transportation fuels. So what is it we need? We would like replacement fuels. Again, economic security, climate change issues, and in many nations, it is really security. That's one of the big driving forces. So we'd like, can we get something alternative? And potentially, it would be awfully nice if it was cheaper. So many different locations have the different opportunities. Climate is very different in many places across the world, and so there isn't one singular answer, of course. It's just a variety of sources and approaches that get used when they make sense. So one of the other alternative sources that is used in places would be coal. And of course, if you fly to South Africa, when you fly out of Johannesburg, you're quite probably flying out on jet fuel that was derived from coal. So you do coal gasification, and then get synthesis gas and do Fischer-Tropsch reactions, and you can produce jet fuel. And so that was certainly done in Germany to make high-octane gasoline for the fighter planes in World War II, and that technology has been continued in South Africa. In China too, they're now doing mostly coal to chemicals, but via gasification. And maybe they could create more fuel that way as well when needed. So, biofuels, we're thinking about biodiesel, ethanol certainly. So these are things you can do right away. The cellulosic ethanol, it's very difficult to take cellulose and convert it to ethanol. So what's easy to make to ethanol is things like sugarcane, sugar beets. So sugar, alcohol, no problem. Cellulose to liquid fuel is a problem. We haven't quite found the right setup that allows us to do that very well. But a lot of research has been put into that, and it's sort of one of the holy grail, because you can grow cellulose, in many other places, and it would allow us to greatly increase our supply of biomass fuels. But we're not going to recreate our fuel infrastructure. We'd like to be able to use existing network, pipes, pumps, etc., etc. And so the property of these fuels has to be as close to our existing setup as possible. So most of you will have taken the refining of crude oil or petroleum processing class. So of course you get a variety of crude oils coming in, depending on where you are and what you're capable of dealing with. Distillation process, and then a whole bunch of changing the quality and the quantity of the cuts through a variety of different processes. And so you've got a whole variety of these fuels that we improve the quality of to get to what it is we would like. So some jet fuel properties. Flashpoint, this is safety handling type of data. This is all fuel properties and handling. Viscosity, at again a particular temperature, because we know there's a temperature influence. Viscosity is important for pumpability. It also has a significant impact on droplet size if you are vaporizing. Freezing point comes down to low temperature handling. Smoke point is a good indication of how much aromatics, such as benzene, might be in the fuel, and an indication of soot emission potential. That of course depends also on thrust, power, engine, etc., etc. So JP8 is currently used. JP900 is a coal-derived petroleum fuel that was done at Penn State. And so Dr. Clifford worked on that for quite a long time. Sulfur we care about because of emissions. Aromatics we care about because of emissions as well. Also a little bit about energy density, but we'll get to that in a second. Thermal stability has to be good. Energy density for these liquid fuels, particularly for a jet fuel, is very key. You need to be able to get a lot of energy out, and that's why we use this liquid fuel, very high energy density. And so 18,400 BTUs per pound, that's more than coal. So it's a very nice energy density. You can get a lot of energy out of burning these liquid fuels. So hydrogen content, API gravity, etc. These are all typical jet fuel properties that you would need to know. And again, hydrogen relates to energy content, and a little bit about carbon content, or a little bit about oxygen too, but mostly we wouldn't have oxygen in our fuel unless it was an alternative fuel. We certainly wouldn't want a lot of it in our jet fuel. and so the hydrogen content is a good measure of energy density as well. So one of the things with jet fuel is thermal stress, particularly at very high temperatures, causes the fuel to break down. And this just shows that with traditional petroleum fuel, jet fuel, that we get carbon deposits, and with this alternative fuel, this coal-based one, that we get much fewer deposits, and that's because the chemistry of the fuel is different. And so the thermal stability was one of the big driving points. Obviously we have a lot of coal, much more coal than we have petroleum, and so these are some of the advantages of using that, and also would allow you to perhaps fly faster and use the fuel as a coolant. Certainly with all the computational power and things like that as well, you need a coolant in the plane, and if you can disperse some of the heat into the fuel prior to burning it, then that allows you to do more and carry more. And so operationally that's also very important. So thermal stability, really this comes down to pyrolysis. Certainly at the high temperature, oxidation, decomposition for the lower temperature range, and you see all of it, but it's really the higher temperature pyrolysis portion that's the more critical, I believe. So here's another good indication of what happens to fuel after thermal stressing. You go from a clear liquid for JP8 to a very dark black liquid. There's various additives that we can add in to try and reduce this this process, but you can see for the JP900, the coal derived, that there is a discoloration, but it certainly isn't all this carbon deposits, this black material, and so you would have less maintenance to do on this fuel than in a jet fighter that was firing JP900. Sorry, JP8. And so there's an awful lot of removing the fuel lines and replacing them after so many hours of operation. It's quite an expense. So we will do calorific value at some point in time. Obviously, you can't have a lower energy density, otherwise you won't be able to fly as far, and you wouldn't have the range that you needed. And so you have to have the jet fuel within a certain select range, and we managed to do that with this alternative fuel. We'll be running a bomb calorimeter later in the semester. Sulfur we'd like to take out of the system. Sulfur in some fuel systems aids with some lubrication type of endeavors, but if you can knock sulfur out, then of course you're not going to get sulfur dioxide in the emission stream, and that's beneficial for the environment. Soot production is something else that you worry about. If you produce too much soot, then you can sort of help melt the metal in the end of your jet turbine. Also, you'd be visible, and it would also aid in missiles locking on to heat sources. But there's also a very large environmental factor as well. We believe that soot really contributes now in a major way to climate change, and so currently research is underway, and we will be adding in pollution control on emissions from airliners in the near future by the APA. And so things like idling and pollution near airports is particularly bad. So this is a very simple test. You just put a fuel supply in a reservoir, and you move a wick up. There's a dirty great big magnifying lens in the front of the window, and you look to see when you start getting smoke in the flame. NOx emissions, of course, are related to temperature, nitrogen in the fuel, carbon monoxide, and all these are mixing issues as well. And so we are also concerned with those emissions. Density we do in two ways, either a hydrometer or a specific gravity bottle. The hydrometer is nice and easy, you just drop it in. It has lead shot at the bottom, and of course some air or other fluid, and it's been calibrated. You're just reading off the density. You need to control the temperature, of course, because that will influence density. The alternative approach is this bottle, and you fill it up. When you put the top on, there is actually a hole drilled in the glass top that's well fitted, and so the excess comes out. You wipe it off, and you can weigh it accurately with some precision, and then get the density that way, because you have a fixed volume. Again, temperature is an important property. So of course there's ASTM standards for specifications, and so it's the D975 is the thing to look at. If you look at fuel safety and handling, flashpoint is certainly a measure. We use the Penske Martin closed cup apparatus in our lab. There are some automated versions as well. Essentially what you're doing is looking at the space above the fuel as it's heated up, and you introduce some energy in the form of a spark or a flame, and you're looking to see when that energy can get propagated across the surface. So you're either looking for a pressure change or a visible flame propagation. So we will use this one, D93. So if you search ASTM, search for D93 and look for the ones that you have access to. And you can look up the flashpoint. So the way the experiment's going to work tomorrow is we're going to say, here's the setup, make it work, and you need to know what you're doing. So look at these methods beforehand. Cold temperature handling is very important. It's cold at the 35,000 feet, 39,000 feet in the atmosphere. But certainly you could take off in Texas and land in Alaska. And of course those would be very significant temperature swings as well. So what happens with viscosity is as you get cooler, you start to get wax crystals. Particularly in things like diesels and biodiesels. In a jet fuel, of course, it's much lower temperature. What we see is a very significant increase in viscosity when you start getting these wax formation and gelling. And so the viscosity becomes very important. And we'll look at viscosity as well. So cloud and pour point are good indications of when you might start to have challenges. There is a diesel chapter in the Angel space. Do look at that because it'll tell you some interesting explanations about how one handles crystals, wax crystals, in diesel fuel in an automobile. There are some interesting things that we can do. So we have both the cloud point and the pour point. So these are slightly different. It's the same setup. It's a glass specimen jar that is cooled in a very specific way, again by our ASTM standards, and we observe when you get initially a cloud. So this is the first indication of some wax crystal formation, as well as when we get a gel that is horizontal for 5 seconds. But again, there's more to it than the setup, and also the frequency of observation becomes important to getting it right and getting the right value. So viscosity changes a great deal. Stokes, Saybolt, universal seconds. So water, it's the 1 Stokes, whereas you get sour cream at 19,000. We've got quite the range, and so different liquids are obviously going to have very different viscosities, and even things like coal tar pitches, things you have to heat up to get them to be liquid, or even ash. We measure the viscosity at even higher temperature of inorganics, relating to how they would flow out of a boiler. So it's important in liquids, it's important in combustion, and so temperature dependency is always an issue. And so keep that in mind. So very simple viscosity endeavor will be a Saybolt viscometer. Essentially there is a chamber, it holds a very specific amount of liquid. It's within a reservoir that's maintained at a specific temperature. Fancy equipment might have heating and cooling, ours just has heating in this particular model. The tip depends on whether we have Saybolt universal seconds or AFRL value. And essentially there's a cork, you pull out the cork, you get a narrow stream of liquid that you've let in for a long enough time period that's reached the temperature. And there is a receiving flask which is marked at a specific volume, and when it reaches that volume, bottom of meniscus, you stop your stopwatch and the time gives you an indication of the viscosity. Some corrections perhaps for the nozzle variations and from calibration too. Again, ASTM might be a newer one. The -07 at the end tells me the year in which it was approved or reapproved. So I think there. So search for D88 and you'll find it. Capillary viscometers are old school. They're still used. We're going to use the Canon Fensky. Essentially, you fill the bulb and then use a suction device to raise the liquid above a certain level and then watch it drain. Quite simple. A lot of these use quite a bit of material. We even have this newer equipment that uses much less and looks at the drop of a small ball within the liquid, and that's very nice because your disposal then becomes much easier and much smaller amounts, so safer as well. So I don't have a Bohlin Viscometer in the lab currently, so we're not going to do this, but you should be aware that there's Newtonian fluids, and so the viscosity doesn't change with shear, but how there are, and I really don't like this term, shear thinning, which is really thickentropic would be the appropriate term, because the thickness doesn't actually change. And this plastics behavior and things like this. So the torque and the viscosity is going to change with rotational forces. So think of sour cream. If you mix it up, it becomes more easy to flow. Or a cream, perhaps, if you're mixing a milk, and then once you create the cream, it becomes harder to stir. Again, so these are behaviors, viscosity behaviors based on a changing shear. So do look up those and ensure you understand what these three behaviors are. And so here's the basic figure that will help you do that, but just spend a couple of seconds. There is a fourth, and that's the Bingham plastic, and that sort of has a yield point. So maybe something like a yogurt that, if you're putting a force in, it's not going to do anything, not going to do anything, not going to do anything, then you're allowed, then you can move your spoon. And so again, spend a couple of minutes just taking a quick look at this. So we do, again, shear in coal tars. So we have to heat up this viscous material. It's a sort of solid, room temperature in some cases, or semi-solid, to get to the point where we can measure the properties. So a little bit about safety. We have heating in Saybolt, so there's some hot liquids potential. Assume all the liquids you're handling are carcinogenic. I think all of them probably are. Certainly anything with the aromatics in is. Depending on what we're handling, we should do certain things in a fume hood. We'll do demonstrations on viscosity with mineral oils just to avoid some of these issues. Obviously, some of the cold temperature work, there's potential for skin damage, so you certainly don't want to touch things that are particularly cold. Flashpoint, you're looking in and you have flames around you, and so particularly those people with long hair, make sure those tucked in. You wouldn't want to have a hair dangle down and catch on fire. Of course, lab coats, safety glasses on the way in, first thing you put on, last thing you take off. So we will see you soon.